Hello everybody, this is another video about the geographically weighted regression. In the first step we did the grid search to get the optimal bandwidth. This time we are going to run the regression itself, slightly differently from what we did before. So let's go to get to work. So the primary libraries needed to perform the geographically weighted regression the multi-scale or MGWR and the related PySARs libraries. The lead PySAR. We also needed GeoPandas to handle geospatial data. The first two provide robust functionality for both geographically weighted regression and the multi-scale geographically weighted regression. The second one is the advanced variant of GWR. So MGWR is the advanced variant of GWR. So after that we needed to have an idea about the world packages needed. Pandas, NumPy, GeoPandas, and GWR, and the data geodata frame with the dependent variable, explanatory variables, and geometry information. That's the coordinates. So we need coordinates, space, geographically weighted, and the information is local. So based on the XY coordinates. Okay, so let's go to Jupyter Notebook and start working. As we had it in the previous video about the grid search, is what you need to have. In addition to what we said before, we need to import point from Shapely geometry, Shapely.geometry. That's to help us get the geodata frame. And the Python. And we need from the MGWR that cell underscore bandwidth, so select bandwidth, import cell that function, and matplotlib.pyplot as PLT. Okay, these are the main things we need to do here, and as you normally should do, so let's go to terminal or command prompt or Anaconda prompt to install these packages before you import them here. So let's run. Okay, now the first steps to get the data into Jupyter. This the same data set wells3.csv found in this directory. So pandas.read underscore CSV. Good. Let's have data. Got the head. We have x coordinate, y coordinate, depth of the well, pH, potential in hydrogen, the sulfate, nitrate, and the temperature. This time we are going to take NO3 as the dependent variable, and our and the variables are still the same, depth and the temperature. So step 2 is to have a geodata file. This is recorded here. Transforming the data frame into a geodata frame. Data transformation. Okay, so here we are going to use another function. Let us be different. We call it GPD, geoconast points from XY. There are some different ways of handling this, so this is another way of doing it. So let's just call it my data equal to GPD geoconast.geodata frame data geometry equal to GPD points underscore from underscore xy parenthesis data dot x coordinate, the first longitude x, and then data dot y coordinate latitude, and of course close the parenthesis twice. So this is our geodata frame. You get here, it's a little bit different from the way we did it in the first video. So my data head, and here we have our geometry. So it's already a geodata frame. Once we transform the data into a geodata frame, we need to prepare our input and output data and the coordinates. Okay, so data preparation, let's get the dependent variable. This is y equal to my data. From my data we take NO3 dot values dot reshape from -1 to 1. précisément here. Okay. Dot values dot shape. Okay, yep. There's a problem with the brackets. So check our y. First rows. Oh, sorry. Y dot test shape, sorry. Step. So it's one column. 100 rows for one column. If you want to print this way, so the print line. And then next is x. The independent variables. Independent variables of x in x. T, temperature, and the total depth of the well, and that values x dot shape. Sorry about that. 2 T in the depth and 100 observation. X gives us our array here. Let's add more rows. Okay, now we are going to get our coordinates. We need the longitude. So u equal to my data x coordinate dot values. These are our longitudes. And v equal my data y chord. That value is these are latitudes. Then you combine them as chords equal to np dot array for the list of zip UV. These are our long lat, long slash lat. Okay, let's run. Let me check something. The row for the values here. Okay, let's have an idea about what is in coordinates as a shape. There's two UNV. Let's paint. Let's see. Okay, these are the longitudes and the latitudes. We can slice here. Okay, let's look at this. Okay, after this we need, of course, now if you have to consider what we did in the grid search before, we have our optimal bandwidth equal to 54. From the first video, but we are going to perform it anyway to use other criteria such as here AICC instead of cross validation, and the kernel is going to be by square. So let's take it 3. Optimal bandwidth. Here we need a selector. Equal cell W chords Y X kernel equal to byte square. Before we took Gaussian, but here this time we take by square and the multi equal to false. Just one. So this is the selector. get the optimal bandwidth. So opt DW optimal bandwidth equal to selector dot search parenthesis criterion. This time we take AIC. So optimal bandwidth. Optimal bandwidth search. It's going to take the time as usual. So it's running. However, we'll continue. Typing in quotes instead of waiting. So we'll print the optimal bandwidth is BW. Okay. This is the step 3. Now the step 4. Step 4. Step 3 is data preparation. So step 1, load the data set. Step 2, data transformation. Step 3, step 4 is liquid search. Okay. Now step 5 is fitting the regression model. Using the optimal bandwidth. Okay, the first thing we need to is initialization as usual. Let's call it GWR model equal GWR capital letter. We have our coordinates, we have our dependent variable and our independent variable. This time we have bandwidth BW, and then we have the kernel. Before we took Gaussian, this one. Let's fill by square. Same here. Okay, so while it's running, we still continue. When we get the optimal bandwidth, we'll come back to it here. Okay. Now, step 6. Adding local coefficients and R squares to the geodata frame. Okay, all of them are local, so the local R squares and coefficients. The geodata frame. Okay, we first add the intercept, local intercept. Data quote bracket quote local intercept equal to GWR underscore model or escape. Sorry, we need the model summary here. Need to fit before. So fitting the model, so initialization, fitting the model. Sorry about that. Let's skip this step. So fitting the model, GWR model equal to GWR model dot fit. Fit on X or fits. Okay. Leave it like this. So, and then we print the model summary. Print GWR underscore model dot summary. Good. Okay, so we're already done. We'll have our bandwidth printed, optimal bandwidth printed. So let's come back around. This is 80. This time we're using bias square and the nitrate as output. Criterion as AIC, we get 80. Bandwidth is what, 80, so it's a little bit higher than 54. And then we feed the model. We initialize first. Oh, sorry. Need to put our 80 here. And run, then we fit, then we have the model summary, and it's here. Model type Gaussian for general observation. Here it's the regression. Ordinary least square regression result. And then we have the R square, which is here 0.066, with the estimates of the intercept, temperature, depth with the standard errors, t-values, p-values. And below we have the geographically weighted regression. We set the special kernel by square. Bandwidth used is 80. So this comparison of these two tables, you have the information you need based on your. This is for this data set, so you're going to have it for your own data set. So here is R square is 0.24 instead of 0.06 over there. So it's higher, perform better than the ordinary least square. And here the most important thing is that you have the estimate per location. XY coordinates over there is just 1 R square, so that's what you have. And the sample statistics as well. Now we add, let's have an idea about my data. Here, let's take my data dot head. You have x coordinates up to geometry, that which we got before. Now we add the local intercept to it. So GWR underscore model dot params. The first we need for params. The params here. The first we have 0 for the intercept. So slice 0. So it's going to add the intercept. So let's take my data dot head. You see, so local intercepts are added. So you need R squares as well. Now let's finish with the two x1 and x2 before. So let's start with t coefficients. Of course, these are local coefficients. My data. T local wave equal to DWR underscore model dot params. We have that's 1 index 1 for temperature is index 1 x1, so index 1 t let's put everything here together. T depth local coefficients data t def question and r square. Okay. Okay, so again we add my data. Def underscore local coefficient local coef equal GWR underscore model dot params, and this time is 2. And then r square is my data local r square local r2 equal GWR underscore model dot r2. Okay, so let's run and have the head of my data. Print it here. So here we have all of our data together in this matrix. Local intercept, T local coefficient, def local coefficient, and local r squares added to the data frame. And now as this is step 7. We have an idea about the partial variation. Visualization. So we are going to look at the r square. First, if you want to change it, we change. So fig x equal to clt dot subplot figure size equal to 10 by 10 then in my data you need let's add more rows here. What you need is the local r square column from my data. So here is my data dot plot. My data dot plot column equal to local r2 color map equal to, let's say, gradis. Region equal to 2. dot set underscore title. Local elsewhere values. Close. Study religion. Not sure. So it's sure to get here. This data square, quite data squares, how they vary from the lowest to the highest. And yeah, you just change here the column if you want. So the columns, you said the local question for temperature, so temperature local question, and we change the title, and we get the result. The map, if you want to read it, cool world. If you want cool world, you change here cool world. You play with it. Okay. And no, the direct way of doing it. It's my data. Dot plot. We have a column equal to let's take T local coefficient, T local quef, sum up that column. So let's do this. And then legend equal to true. So this is for local coefficient for temperature. For the varying depth local coefficients. If you want, is intercept, local intercepts, right? So it's local underscore intercept. I think that's how I wrote it there. So these are the values of nitrate when there is no input. What it means, the latitudes. So we have the longitude here, the latitude here, and these concentrations of the nitrates when there is no temperature, there is no depth, the no impact of depth, no impact of temperature at all. So these are the values. And then for increase of temperature, it modifies. So this is going to plus x0 plus x1 beta 1 x1 plus beta 2 x2. So you know the regression equation. So we are at the end of this video. Thank you very much for watching it. I hope it will help some people who are doing research in spatial regression. So we need to try several models and figure out which one really fits your data, gives to give you a good result. Random forest, regression tree, OLS, geographically weighted regression. Here already you have results from ordinary least square and the geographically weighted regression, and we see that geographically weighted regression performs better than the ordinary least square. So we try again one of our whatever you have as model that you can run using special data, and you select the best. That's the purpose, but you put everything in your result. Okay. You get the results about all the models you use and the one that performs the best. You put all of them together in the, if you want. It's what is the purpose of your research? To publish a paper or to do for application purposes. So hope this video will help. So thank you so much, and see you next time for another video.